3, 2, 1. All right, and away we go. A lovely pre-recorded video on this wonderful Pi Day. All right. Okay, so what's the plot for today? So last time we went through some examples of vector spaces. We went through the sort of the classic examples of Euclidean space and matrices, and then from there kind of noted that they're both actually kind of examples of the vector space of real valued functions on just some set. And then we looked at some weirdo examples, my favorite crazy vector space example. And then we finished by defining what a subspace was. And so today we're really going to dig into what subspaces are and the various ins, outs, and what have yous. All right. Okay. So let's just jump right back to the definition where we ended off. So given a vector space V, a subspace is a subset of the vector space with the following three properties. First of all, M has something in it. It's not empty. Next, a subspace is closed under scaling, meaning that if you are in the subspace, you cannot escape the subspace by scaling. And similarly, if you are in the subspace, you cannot escape the subspace by adding. All right. Okay. So what was our motivation for this definition? Right now, of course, we've seen examples of math objects that have these properties, right? The four fundamental subsets of a matrix, the null space, the column space, the row space, and then the orthogonal complement of the column space, also the null space of the transpose. All four of those sets possessed precisely these three properties. Ah, nice. Okay, and our motivation for this was coming from our example list where we went, all right, well, we've got some examples, and it seems pretty involved in verifying that something is a vector space. So we would love it for a more efficient method of creating vector spaces, and since we already have examples of pretty sizable vector spaces, it'd be great if there was a way to create vector spaces from ones we already know. And a subspace gives us the classic way of getting it, where, as we are going to see in a moment, these are precisely the subsets of vector spaces that are vector spaces in their own right. Okay. So the thing to note here is that note that M is in fact equipped with a scaling and an adding. Specifically, it's the scaling it is the scaling and the adding of V, right? So M is equipped with, given an element X and a scalar alpha, alpha X is defined in M. And likewise, given an X and a Y in M, then the summation is defined in M, right? It's the summation from V. Okay. So, our first goal is going to be verifying that M itself becomes a vector space. Alright, and if I just knew how to spell, which I obviously don't, there we go. Alright. So that's our first goal for today, is to verify that, indeed, as claimed, these are the vector spaces within vector spaces. So our first goal is going to be prove that subspaces are, in fact, vector spaces themselves. Alright, now, right off the bat, as we kind of noted, because we have this addition, and this addition came from the vector space V, we automatically are going to get associativity and commutativity, because this symbol has those properties for any element in V, and M is contained in V, so all of the elements are there, and there you go. It satisfies them, right? Nothing crazy or interesting there. All right, and then similarly, literally all of the scaling axioms are going to be for free, because the scaling here, right, behaves in V, and any element out of M, right, the scaling is going to behave nicely. So 6 of the 8 axioms are just immediate and don't require any real justification. However, we know vector spaces are equipped with other things. Specifically, they are equipped with an identity and an inverse. All right, so our first goal in verifying that a subspace is a vector space, we need to establish a couple of facts about subspaces, and in particular, if I'm claiming they're vector spaces, they have to have an identity. Right. So that means if I'm claiming that M is going to itself become a vector space, it's going to have identities. It's going to have to have an identity. It's going to have an inverse. Now, we already have an identity in V, and we already have inverses in V. So, right, it's going to behoove us to just use those rather than wholesale create new identities or new inverses. All right, so V is a vector space and M is a subspace. Indeed, it has to be that the additive identity lives in the set. And furthermore, given any element that lives in the set, its negative is in the set. And there we go. That takes care of the two other axioms that we need to be a vector space. So as noted, and we'll formally write this proof out in a little bit, since the addition is coming from a vector space, we already have the associativity and the commutivity. And since the scaling is coming from a vector space, all of the scaling axioms are just going to be for free, right? No effort on our part. The only thing that we're going to have to put a little effort into here is actually verifying that we have the additive identity and additive inverses. All right, so how are these proofs going to go down? All right, well, it turns out that there's actually a couple of ways of verifying both of these facts. All right, so M is non-empty. And what does that mean? Well, that means that we have access to something. So, by hypothesis, there is some X that lives in M. Let's use, well, I'm going to use X here. Let me use a different letter. Let's use A. By hypothesis, there is something in the set, right? That's what it means to be non-empty. There is something in the set, period. All right, well, I want to show that this belongs to the set. Now, how can I get this in the set? All right, well, one of my other hypotheses here, one of my hypotheses is that I'm closed under scaling and I'm closed under adding. Okay, well, I only have one element. I don't have multiple elements here, so I probably am going to have to use the scaling assumption. And indeed, there's a really slick way of proving this. Well, by hypothesis, we're closed under scaling, and note that's for every real number, so we can scale by our good friend 0. And as we've already proven, scaling by 0 gets us the additive identity. So that means that the additive identity, indeed, absolutely has to be in the set. Okay, so note here we proved that you've got the additive identity by scaling by 0. Really slick trick. Okay, now, pretty neat proof. Now, I want to do a different proof of this fact using the additive properties. Okay. So I'll do sort of an enumerate here. So we'll say 2 techniques. So I want to do. I want to point out that there are 2 ways of proving this. You can use the scaling assumptions and you can use the additive assumptions. So if you let your mind float back to when I took this class a very long time ago, nearly 20 years ago when I took this class, I remember that this is actually a homework problem for us. We actually had to prove that if you've got a subspace that the additive identity is in there. All right. Okay. And this is not the proof that I came up with. So I went to office hours with good old Professor Fulton, and I had my little proof, and I showed him. I'm like, hey, here's how I proved it. And he went, yeah, that's right. That's good. Yeah, good proof. But I was in the office hours with my friend Jake, and Jake said, well, that's not how I proved it. And then I was like, oh, how'd you do it? And then he was like, well, it's closed under scaling, so I just scaled by 0. And I remember I got like, in my head, I got like so mad at him. I was like, oh, that's so stupid. Because the proof that I had was the following. The proof that I did was this. So I used the both of the hypotheses. I used both the scaling and the adding. So the method of attack that I did was the following. Specifically, using the fact that scaling by -1 gives you the negative, and and then I've also got addition, so you can put them together like that. Right. So this was the proof, more or less, that I had put together and presented, and I thought I was really slick. And again, I thought this was like the right proof because what did I use? I used all three hypotheses, right? I used, hey, M is non-empty, we're closed under scaling, and then we're closed under addition. Right, so I was like, hey, that has to be the right proof. I used all my assumptions. Yeah. So I wasn't even thinking of trying to cheese it by using less of the hypotheses. So either of these are totally valid and get you that indeed you have the additive identity, but it doesn't matter which way you go. All right, and note here, side note, we've already sort of spoiled point number 2. That's how you prove point 2. But again, there's actually sort of two techniques here. Well, there's really just the one, I guess. Indeed, if X is in M, then the negative is in there. So, note that I kind of used it. Scaling by -1 gets you the negative, so yeah, obviously you're in there. There you go. Okay, so note for point 2, that's sort of implicit in one of the techniques here for point 1. There you go. Neat. All right, so with these demonstrated, we can then prove the property as claimed. So let's take a vector space and a subspace. All right, and the way we will claim this is as follows. Let V be a vector space and let M be a subspace. Then M is itself a subspace. Then M is a vector space. When equipped with the addition and scaling of V, right? So as we already noted, this has a scaling and an adding, right? Clearly, as claimed. But, right, why is it actually a vector space? And we now have all of the ingredients for this, and let's do the proof. Okay, so again, we've got 8 facts to verify. I wasn't yelling at. Oh, I didn't spell proof right. I wrote proof instead of proof, and now the box is there. All right, so again, we have 8 facts to verify. And as we sort of already noted, we already kind of had a bunch of them for free, right? The addition came from V, which is a vector space, and that addition is associative, so that's automatically true. No effort. And similarly, the next adding axiom, the commutivity, is also for free because the addition came from a vector space and it is by definition commutative. All right. All right, and then next up, there exists a element that belongs to M, such that that holds for all M. Let's write it that way. There exists. All right. All right, so the third adding axiom, there is an additive identity, and in particular, the additive identity of M is the additive identity of V, right? So there is an element with the property we want. Okay. And now that we have an additive identity, we can talk about additive inverses, and by the previous proposition, we proved that if x is in M, then negative x is in M, and thus we have additive inverses. Hey. Right, so these were the only two of the additive axioms that required a little bit of work on our part. We had to actually individually prove that stuff, but with it, we are good. All right. And then finally, we have our scaling axioms that we need to verify, but the scaling is coming from a vector space V, so all of the scaling axioms just will pop out for free. Yeah, that works for all x and y out of M, because all of them came from V, right? They came out of M, and M lives in V. Similarly, the conversion of scalar addition to vector addition holds, because again, everything here is elements out of V. So, right, even though that they started in M, M is contained in V, and so we are good. The axioms hold. And finally, the multiplicative scaling will go through the way it's supposed to, and the scaling by 1 goes through the way it's supposed to. All right. And there we go. We now have access to the following. If you've got a subset with these various properties, scaling, closure, addition, closure, and being a non-empty set, then congrats, you got a vector space. So, if you want to create new vector spaces, well, look at a vector space that you already know you've got access to, then you only need to check 3 axioms that will verify that you are a vector space. Nice. So this gives us a much more efficient and simpler way of establishing certain vector spaces. All right, so equipped with this, let's get some examples of vector spaces. Alright, so equipped with this, we can create some more vector spaces, because now I just need to start with a vector space that I already know about, and then just create a subspace. Alright, so let's look at probably the most famous example here of something like that. Right, so we will go ahead and let Alright, and so the notation I'm going to use for this is the following. We will let R, close bracket, x, be the set of polynomials. So these are functions, and for us these will be real valued to real valued. Or complex valued, depending on what we will need to look at. Alright, so let's include that in the notation. So this is the symbol we'll use for the set of polynomials. We can also write C of x if we need to do complex valued stuff, which will show up because a little bit later on in the course we're going to need to take roots of polynomials, and we know complex numbers show up when you do that. And let's recall what are polynomials again. Well, these are precisely the functions that look like this. Alright, so they are the functions that are things that look like alpha naught plus alpha 1x plus all the way up to alpha and xn. Right, so we know quadratics, we know cubics, quartics, so on and so forth. Okay. Right, easy to verify. Easy to verify claim. So this is in fact a subspace of the set of real-valued functions coming from the reals, and it's pretty easy to verify that it's a subspace. So let's sort of quickly do that. And note that if I wanted to verify this subspace, there are a couple of things to do. Alright, so I'm claiming it's a subspace, so I gotta verify three things. That it's non-empty, first of all. And note that the constant function 0 counts as a polynomial. Right, that would be the case where the n here is equal to 0, and, right, the a0 is 0. So that belongs to the set, and there you go. And note something here. Hey, I wanted to verify it's not empty, and typically what you will do is actually show that it's the additive identity that's in there. And in a little bit here, we'll talk a little bit more about subspaces and some other ways of demonstrating that something is a subspace. Alright. Alright, now given a polynomial, p of x, which is equal to a0 plus a1 x plus up to an xn, and given a scalar, then if you look at alpha p, what happens? You'll just get a scalar multiple of a polynomial, and note that what you'll get is exactly a polynomial. Right, the coefficients are just getting scaled. That's it. Alright, so, there we go. And let's new page that. Alright, so the set of polynomials, if we're looking at, again, we're trying to verify there's a subspace of the set of real-valued functions from the reals, and we are verifying our three facts. Alright, so the constant function 0 is a polynomial. Given a polynomial and a scalar, well, if we look at alpha p, again, by definition that's that, and that gives us that. Alright, and note, that's a polynomial. Alright, as we noted, scaling functions works as it did from our calculus days, and here we see if you scale a polynomial, it remains a polynomial. And then finally, if I take two polynomials, and now here's where we are going to have to be a little bit careful. If I take two polynomials, note that their degrees do not need to be the same, like that. However, if I were to now look at their summation, p plus q, let's get that in there. If we were now to look at their summation, p plus q, well, what's the output? The output's p of x plus p plus q of x. And let me go ahead and... Alright. And I'm going to make this in a line, because I don't think I'm going to have enough room. Let's go ahead and do that. Alright. Okay, so when we add these up and look at them... There we go. Great. Alright, so p of x's output is that, and q of x's output is this. Now, n and m are potentially different from each other. However, there is a maximum between these two, right? One of these is bigger than the other. Alright, and when you add them up, well, then everything is going to line up, and we will go ahead and get something that looks like this. right, where the capital M there is going to be whichever of the N and M is bigger, right? So you just find the biggest one, and then when you add them all up, all of the terms will line up and add up, and you'll just get something that looks like this. Right, now if you want some like explicit formulas for the coefficients, you can do that, but right, it's easy enough to verify that, yeah, when we add these two, it's going to collapse down to a polynomial, where the power we see here will be whatever's bigger between N and M. Alright, nice. Alright, so consequently, it's closing or adding. Alright, sweet. So there we go. The set of polynomials is, in fact, a subspace of our vector space of real-valued functions, and thus we know now that this is a vector space that we can work with. Exciting. Alright, let's get another example. Alright, so a similar one and a offshoot of this is the following. We'll let R sub n be the polynomials of degree less than or equal to n. Alright, now what does that mean? So note that before, if P was so let's write it this way. So note what's the difference between this set and this set. So note that if P is in there, then and I'll use a different n here. So note, to be in the set of polynomials, there is some n, so that you look like this. Whereas P is in R sub little n, if and only if So noting the difference really here between these two sets, the set of polynomials is you're in there if there is some n that works, whereas you're in this one precisely if you always go up to this n, or, right. So note that to be a polynomial, there is some n that you add up to like that. However, here we are requiring that what you are is something of this form. Now, again, note, I'm not requiring this term here to be non-zero. That's the less than or equal to part of it. All right, so noting the difference between these sets, you're a polynomial if there is some n that works. However, the only way you're in this one is if we can always go up to that n. Right, so for example, 1 plus x cubed is in, so let's do, for an example here, I'll do a center on this one, so we're good. Alright, so for example, 1 plus x cubed belongs to the set of polynomials. Nope, it's going to yell at me. Alright, so that belongs to the set of polynomials, but what other ones does this belong to? Alright, well, it belongs to, obviously, R3. Right, because, yeah, it goes up to 3. Now note, it also will belong to R4, right? It will count because its degree is less than or equal to 4. So it's also in R4, but right, obviously, you're right, your first thought would be like, well, this is the one it's really in. So, but it's in these larger ones as well. However, note that 1 plus x cubed is definitely not in R2. right? Its degree exceeds 2. All right, so hopefully that clears it up a little bit as to the notation, right? If you're in this set, there is some n where you're equal to this, and being in this one, we're requiring that you go up to that n, but it's possible you fall a little short of it, right? You can be in R5, right, but you're just like x plus x squared. That counts for R5 for sure, but you would naturally think of it more as an element of R2. All right. All right. Anyway, similar argument. All right. So a similar argument will reveal that this is in fact a subspace of the set of real-valued functions. So it is a vector space in its own right. But what's also interesting is that it's also a subspace of all of the polynomials, which is really neat. So note here, right, this is a vector space, and this is a subspace that can be verified, but note that this belongs to the set, it's a subset of this one, and this is a vector space in its own right, but note the vector space operations came from this set, so it will also count as a subspace for this sort of intermediate set. It's kind of neat. All right. Cool. All right. Now, what's another example of a subspace that is worth our time? Well, another great example. So here we have two classic function examples, and we will come back to the set of polynomials here and there, specifically the set of polynomials of degree less than or equal to n. We will note that that set is quite nice and has some nice vector space properties. But let's now bring in some matrices and talk about subspaces that those things generate. All right, so let's take an M by N matrix. And let's note that we've already sort of established that we have a subspace associated with any matrix, right? The null space, so the set of solutions to the associated homogeneous equation. This is a subspace of Rn. So let's note that we actually, in fact, already demonstrated this, right? When we were talking about our fundamental subsets of a matrix, we noted that, hey, all of these are closed under scaling and adding. And they're all non-empty, right? Obviously, for a homogeneous system, you always have a solution, the trivial one, x equals 0. So, hey, now we know this is a subspace, but what's really neat about this one is the following. This lets us construct some pretty neat subspaces of Euclidean space and thus create some pretty interesting vector spaces. Consider the following. So let's go ahead and look at the following subset of R3. Alright, so let's look at the following. Alright, so I'm going to create a set, and we're going to hang out in R3. So note here, I've got my X, Y, and Z going on. Alright, and I'm going to look at the following. I'm going to look at the situation where I've got an x, a y, and a z, and I've got the following relationships between them. I know that x is equal to y plus z, and I also know that y minus z has to equal 0. All right. So, all right, I've got this going on here. I have these elements of R3 with the following property. I know that x is equal to y plus z, and I know z minus y is equal to 0. All right. Now, hey, this is just some subset of R3 that I created. However, we are about to do a neat little sneaky. Let me define a matrix. I'm going to make the following matrix. And the entries of the matrix might be immediately obvious as to what's about to happen, but maybe not. All right, so define the following matrix here. Hey, looky here, I made a 2x3. Now, given any x out of R3, what happens? Well, what happens when I multiply any element in R3 by this matrix? Let me rewrite it this way. Alright, so note that if we were to take our matrix A and multiply it by any vector out of R3, and let's take our elements out of R3 to be the vectors x, y, and z, like that. Alright, well, let's do out that matrix multiplication. Alright, note that this is a 2x3, so I can multiply it by elements of R3. And if we do that, compute out those dot products. Right, so in the first spot, we'll have x minus y minus z. And in the second spot, we'll have y minus z. Alright, so note that when I look at a times any element of R3, I get, oh, hey, these equations right here. And note, when is this vector equal to 0? Well, when that's equal to 0, which will be, oh, precisely that. And when this is equal to 0, which will be, oh, hey, precisely that. So note here that vector, that subset that I created is actually, in fact, the null space of this matrix. Oh my god, what was it yelling at me about? Oh, no, the slash. That's the... There you go. There you go. Hey. Alright, neat. Hey, so this thing right here has to be a subspace of R3. And note, I didn't need to go through and, like, verify any of my axioms, right? Because I just know, hey, I can turn this into a null space. And if I turn it into a null space, I know it's a subspace, and so, boom, there you go. We immediately know it's a subspace. Now we know that this set is, in fact, a vector space, in its own right. It's a pretty interesting vector space. Cool. Very neat. Okay, so this lets us now create subspaces pretty easily in Euclidean space. So we created these pretty interesting subspaces in the world of functions, and now here we see that in Euclidean space we can make some pretty easy subspaces using null spaces. And let's wrap up today by pulling a similar maneuver, but with column spaces. Alright, so let's recall our friend, the column space of a matrix. And let's recall where this lives. This lives in R3, right? So remember, this is the span of the columns. And so if you pick a column and lock it down, it has m entries, so this is a subspace of R3. Alright, so I want to make subspaces using this then, so let's consider the following. Alright, let's make a subspace of R4. Alright, so let's pick a situation where we have x, y, z, and w. And, no, so let's make it more interesting. Just an x, y, and a z. Alright, let's do x minus 3y, let's do 4y plus 2z, let's do z minus x, and then let's add them all up. Alright. Sweet. Alright, So now let's consider the following construct. So, alright. Note here now we have these vectors that live in R4, but this is good for x, y, and z out of the reals. So in the first component, it will be x minus 3z. So pick any two real numbers, x and y, and look at that. So, and then here we pick these three real numbers. Now in the second coordinate, you're looking at 4y plus 2z. In the third coordinate, you're looking at z minus x. And in the final coordinate, you're looking at x plus y plus z. All right, so let's go ahead and pull a similar thing that we did here. Let's go ahead and define a matrix. All right, so let's go ahead and create a matrix A. And what should the entries of this matrix be, you think? All right, well, let's note, I've got, in a way, we can look at this and go, hey, I've got 3 variables and 4 equations, basically. So I'm probably going to make a 4 by 3. All right, and indeed, it's pretty easy to see what the entries of the matrix that we will need here. All right, and so let me make this. Oh God, what is it yelling at me? Oh, I don't have an end equation. Doing good. All right, and hey, looky here. This matrix right here, well, what happens when I multiply this thing by an element of R3? Well, what happens when I multiply this matrix by... Alright. An element out of R3. Anyway, well, when I do that... Alright, well, if I multiply this thing by an element out of R3, like this, well, then we compute our dot products, and then conveniently, what are we going to get? Well, you're going to get precisely this set of equations right there. Right, so indeed, write it out, right? So row 1 dotted with column 1, so it would be 1 times x plus negative 3 times y plus 0 times z, giving me that equation there. And similarly, you do that for the second row, the third, and the fourth, and you'll get all of those. And hey, that lines up with that exactly. Now, before we created these things, and with those equaling 0, lined up with these fundamental equations there. Here now, right, we just sort of have directly that, yeah, a times x is equal to that, and recall that's precisely what the column space is. It's the collection of all things that look like a times x. So this thing right here is in fact now a subspace because it is actually a column space. All right, indeed, so this is just the column space of a matrix, and thus this thing is a subspace in its own right. Ooh, pretty cool. Right, so this actually now reveals that it's pretty easy to concoct subspaces of Euclidean space using matrices, right? And depending on what I want to do I want to have sort of equations like this to work with? As long as those equations are nice and linear, there is a matrix that will give me the null space for it. Or do I want to create things that have like sort of direct equations in the coordinates? Well, then that's a column space. And there we go. We now have some pretty interesting examples now. Cool. Right, and again, this reveals that this itself, this object right here, is in fact a vector space when equipped with the operations of R4. And similarly, this object right here is a vector space when equipped with the operations of R3. Beautiful. All right, really, really cool. All right, so what's next on the docket? All right, well, we've introduced the notion of subspace. We proved that subspaces give us a method of creating vector spaces. All right, and equipped with that, we now were able to identify some subspaces in the set of functions and hanging out in Euclidean space. And so now we've got sort of a profusion of examples. So what's the story for next time? Well, next time we will talk more about properties that subspaces will have. Now that we have a bunch of examples of them, let's go ahead and dig a little deeper and see what are some things that subspaces do. And we may note that, well, wait a minute, this thing was a span, so maybe we need to talk about spans in vector spaces. Ooh. All right, so that will be the plot for Monday. That was it for today. Hope you enjoyed, and I will see you next time.